Let me see if any of what we've talked about has sunk in. So we're going to do an example first to see what has sunk in and what hasn't. So I want to be careful when I draw this, so give me a moment. Look, I got everything plugged in the way I'm supposed to. If you can't see it, that's your fault. Good, Mr. Shelton. Way to talk to your students. All right. I have a skateboarder who begins at the top of a ramp. The heck are they doing up there at the top of that ramp? Let's make them look a little bit more boring. There we go. Skateboarder at the top of the ramp. The ramp itself is 4 meters higher than the ground below. And they are moving at 2 meters per second. There is a platform 2 meters into their motion. We'll call this point A, and another one at point B. I would like to know the velocity of the skateboard at both A and B. Now, before you guys launch into it, I want to tell you that this is a clear conservation of energy question. You can tell because there is an obvious change of height, suggesting that there's a change in gravitational potential energy. Do your best to figure out the velocity at A and B. And note that I have purposefully not given you the mass of the skateboarder. All right, a quick loop of the room kind of shows me 2 different groups. At least last period there was 3 different groups, but this room shows me 2 different groups. A group that could get started right away and knew what they were doing, and a group that has no clue. So I'm speaking to you no-cluers. There's a clue here. If there's no force of friction or air resistance, if there's no force that takes energy out of the system, then the energy in this system stays the same. Which means at the top of the ramp, the energy of the skateboarder is the same as at point A, which is the same as at point B. My job now is to try and find a way of figuring out all the different forms of energy my skateboarder could have at those 3 locations. Considering that list involves only 2 items right now in our arsenal, it shouldn't be hard to list them. For example, is the skateboarder moving at the top of the ramp? If so, then my skateboarder has kinetic energy. Is my skateboarder above the lowest point that they are likely to attain? The answer is yes. Then my skateboarder has gravitational potential energy. At the top of the ramp, my skateboarder has 1/2 mv squared worth of kinetic energy. You know how fast they're going. And at the top of that first ramp, my skateboarder has mg times 4. Because it's mgh, the height above the lowest point that they are likely to attain. This is the amount of energy that my skateboarder has at the very top. Now, that alone tells me very little unless I was asked for the total energy of the skateboarder, which I was not. And I would not be able to answer total energy of the skateboarder because I don't have the mass. Put that in your notes. That in some cases I might not need the mass, but I would need it to figure out the total energy because mass is in both of these. However, I purposely didn't give to the mass so you could see something else. And that is, consider the skateboarder when they've made it to point A. When they've made it to point A, do they have more potential energy or less potential energy? Less. They are lower. So mgh is less joules. But the total energy has to stay the same, which means that energy becomes kinetic or goes into some other form, but I see nothing else here where we could trace that energy, so it's kinetic. That's always the default for any of that extra energy goes. Which means that at A, I have kinetic energy and potential, and the amount is going to be 1/2 m v squared. I don't know how much kinetic there is because I don't know how fast they're going. I do know, though, it's going to be m, g, h, where h is 2. Now, for conservation of energy, those two have to be equal. All of this has to equal all of this. So 1/2 mv squared plus m times 40. Oh, not v squared. I can go ahead and put 2 or 4 squared in there. Sorry, m times 2 squared plus m times 40 equals 1/2 mv squared plus m times 20. The energies have to be equal. This is where you should note that since every term has an m in it, I can factor out and remove it, assuming it's not 0. And I doubt the mass is 0. I wouldn't have an object then. 1/2 times 2 squared is still 2. Plus 40 is 42. So this is 42 equals 1/2 v squared plus 20. So v equals, is that 6? It's the square root of 44. I think it's more than 6 and less than 7. So nobody got this far? 6.6. You guys are going to need to step your game up. All right. Find point B. Be prepared for me to call on one of you. The one without the calculator in hand is probably the most likely. That's what it seems like to me. It's hard for me to say that these are challenging questions, but it does seem like you guys need a little more practice. So here's another piece of practice. Start with let's see. So I have a ball that's being thrown upwards. It has a mass of 0.5 kilograms. It's being chucked upwards at 20 meters per second. I'm going to ask you 3 questions. Question A. What height will the ball's energy be half gravitational? What height will the ball velocity be half? And C, what is the max height of the ball? Okay? All right, get it done. Practice.